We are continuing to look at digital hardware circuits in the computer. The next component we're looking at is the half adder. The half adder, as the name implies, is a circuit that generates the sum of two binary digits. It has two inputs, A and B, and two outputs, the sum of the two digits and the carry bit. The half adder can be implemented with one exclusive OR gate, seen here, and one AND gate. So this is the truth table for the half adder, and really all we're doing is adding the two bits together. So if we click on A, it lights up the sum, so 0 and 1 is 1. If we do B, again, doesn't matter, commutative property, which order we add them in, 1 is still 1. And then the fourth possibility here is 1, 1, which has a carry bit, right? So it should be 2, but we only have is a 1-bit half adder, so we have a carry bit. Okay. The next circuit we want to look at is the full adder. And so as we pull it up, we can see that this adder has three inputs. So the A and B, just like last time, the data bits, and we have one that is the carry in. The carry is used to carry the bit from the previous operation in the lower significant digit position. And then the two outputs are again the sum of the two digits that are input. And if there's a carry, then a carry bit. Okay, and so we can use these adders in series, so we can, at each significant digit gets higher, we can pass from lower. So we'll pass the carry bit from one adder up to the next adder. But let's look at just the one adder by itself, and what we'll do, again, just verify the operation, and then if we have 1 and 1, of course we get a carry bit. Okay, so again, two XOR gates, two ANDs, and an OR gate to implement the full adder. Let's take a look at a little bit more practical example where we have a 4-bit adder. And what we've done is taken this logic for our full adder, and we've incorporated that, or created a level of abstraction where we put all of that circuit inside this box, and we're just going to call this box an adder. Notice the inputs and the outputs are the same. We have the three inputs, the carry in, A and B. Now we designated A0, B0 because these are the least significant digits in the number, in the 4-bit number, and then A1, A2, A3 for the first number, B0, 1, 2, and 3 for the second 4-bit number. The outputs again are the sum 0, the sum of the least significant digit, up through S3, the most significant digit, and each adder has a C out, okay, or a carry out that is just fed into the carry in of the next full adder. And then if we have an overflow or a carryover from our last position, we've got this one last carry out indicator. So if we just put in a 1 plus 0 for B is just 1. If we go ahead and put in B as 1, we should get an output of 2. Okay, so we've got a carryover, and if you can imagine in the positions, S0 being our first position, 0 and then 1, which is 2. So 1 and 1 is 2. If we take off of 2 and we add in a 2 for B, 2, okay, plus 1 is going to be 3. So we have a 1 in the first position and 1 in the 2's position. So 2 and 1 is 3. So this is how we implement a 4-bit adder. If you needed for your project to implement a larger adder, say 8 bits, we could duplicate this whole thing and just feed the carry out into the carry in of the next level. So you can add as many bits as you need for the adders. Okay. And the next one we look at is called an incrementer. And I did in this particular simulation use, these are full adders. We don't need that. We can use half adders because we really don't have another number B. So the whole purpose of an incrementer is just to increment a value by 1. Okay. And so what we do in the first adder, again, we've got all zeros for A, so 0 plus 1. So we feed in a constant here of 1. You could consider that true, but normally in binary we think of it as 1. Some simulators might use the value of true instead of 1. This one uses 1. Okay, so it adds 1 in. If we change our input data to 1 here, it adds 1, so we get 2. If we change this to 2, again, the increment is adding 1, so it goes to 3. If we go to 3, again, it adds 1 in, so it goes up to 4. Okay, and so on, so on. If we continue, we eventually get again a carry out, so we overflowed there. So so that's just a basic increment operation. And let's close these. The next one we want to look at is a little bit more complicated, is the ALU, or arithmetic logic unit. And that's the circuit that performs a set of arithmetic and or logical operations on the processor. The ALU is going to have a selection line that's used to select the operation to be performed. So in this example, I've got a 2-bit ALU. So if we just focus on the first part right here, this is kind of demonstrates the function of a 1-bit, and then we can have other lines for a 2-bit, and then so on. You can add the logic to add as many bits as you need. So just focusing on this first part, we can see that we have two inputs, A0, B0, and then we have over here the selection bit that goes to this MUX multiplexer. And so this selection is going to be used to select an operation. Okay, so what operations? This is a not too complicated circuit if we look at it. So A and B, the first operation we're going to look at is this XOR right here, okay, or exclusive OR. So again, that's going to be fed into the first input of our multiplexer. And remember, the multiplexer is going to take multiple inputs and then convert it to one output. So if we have a 0 selection, we're selecting the first circuit, okay, which is our 0 input. So it's going to do an XOR for A and B. The second one is going to be just a simple AND, logical operation. The third one is a simple OR. The next one is just NOT, but it's a particular NOT. It ignores B as the input, and it just takes the NOT of A. Okay, so it reverses that bit. The next one is going to be almost the same, except for ignores A and gives us the NOT of B. And then the next operation is actually a full adder here. And there's one output to this whole full adder circuit. That's this operation right here. A little bit more logic. I could have simplified this and put it in one block, a full adder. But I wanted to show a little bit of the complexity. And then, of course, for the adder circuit, we're going to have a carry bit that'll go down to our adder in the second bit. Okay, and we could extend this for as many bits as we want if we just keep going down. But this should demonstrate our purpose. Our outputs to this, the output of the first multiplexer is going to be the least significant digit of our output, bit 0, and then from the second multiplexer we'll have the next, and that should be out 1 instead of out 2. And then we'll have a carry. The carry bit is just if we're doing the addition operation, we can potentially get a carry. So let's put some data in here. I'm going to just go ahead and put in 1 for A, and it's doing an XOR, so we get a dot there. And then I'm going to say, let's say the next most significant digit for B. So we've got 1 for A and 2 for B, okay, in binary. So we get, for the exclusive OR, we get both of those lit up. If I pick the same, it'll unlight those again for exclusive OR. So let's go down to our selection code here, and I'm going to select 1. So that should select our AND. And so we get nothing lit up because 1 and 0 is going to be 0, 0 and 1 is also 0 for the second output. Just to check it, we do 1 and 1. Hey, 1 and 1 is 1. So we got that. Let's change this to 2. And now we should be selecting this line right here, the third line, but number 2, 0, 1, 2. And that would be an OR. And so both things light up because we have 1 or 0, and then 1, or 0 or 1. So they both light up. To make one not light up, we need both to be 0. And so that works out. So we've selected our OR circuit. Next one would be number 3. So I'm going to put 3 in our selection code here. So now we're doing a NOT, but remember it's just a NOT of A. So I have 1 for A, it changes to 0 here, 0 changes to 1. 4 is just going to be same thing, but for B, okay, that NOT. And then the last selection, if we select binary 5, we're selecting this last gate here, so we should have an add. So if we do 1 for A and 2 for B, we get 3 as an output. So let's do 1 and 1, we get 2. And so if we select these 2 digits on our 2 multiplexers, we're selecting this add circuit down here. So that's kind of the gist of how an ALU works. There are different designs depending on what you want to do. So here's a different example of one, and this one's a little bit simpler. Although we've kind of have a level of abstraction here. We have an adder in here. So here's one of our selections. We have an add and an AND. So let's put some data in here. I'm just going to put 1 and 1. And on our output, I have the 0 selected, which is the add. And so it's adding, okay, 1. 1 and 1 is 2. So now if I wanted to AND it, 1 and 1 would be 1. All these zeros would be 0. So let me change the selection on this one. And instead of selecting this adder here, I'm going to be selecting the AND gate down here. So just a logical AND, which it does. So 1 and 1 is 1. All the rest are zeros. The other thing I can do, though, is I have these 2 multiplexers here that can select from the 2 inputs either the direct A and B, or I can also negate the input of A or and or B by selecting these 2 inputs or selections for these multiplexers. So let me go ahead and negate A. And so it switches. So when you negate it, now it's 1, 1, 1, 1, 1, and then this becomes 0. And so when we're doing that as a AND, our output's all 0. So to change that, I could go over here and add this, or if I switch all these around, again, it's negating it, so you end up with a 1 here and all these zeros with this not. If I switch this back to add, I should be adding 1 back in, so I get 2. Okay, so a little bit different example of an ALU. This one is probably a little bit more classic example, but there's all different kinds depending on the design and what you're trying to do. So hopefully that helps, and we'll continue on in the future with more examples of this.